word on this. So I wanted to talk about, it'd be a fairly short lecture because I'm going to try and actually go through the process of creating a hello world under Code Composer Studio and then running that on our microcontroller board today. So this section is an introduction to C. I recommend that you read this. I am not going to go through all of this section. It spends a lot of time talking about operators in C, but whatever language you've used before, C or C#, the arithmetic operators, the binary operators are the same for Java, C++. So I'm not going to go through all of that. I'm going to touch on a few things. The first is, a C language statement like Z is equal to X plus Y. Okay, it might be a statement you would have in your C source code file. Well, we're going to spend some time in here programming in a lot in C, but also in assembly. Okay, what C does is kind of hide the microprocessor architecture from you. Okay. In assembly, you have to know the microprocessor architecture, how many registers it has, what the names of the registers are, what the various instructions are that are supported by that microprocessor. So this one line in C at the assembly language level, you might have to do several different instructions. X representing a memory location, and this is probably not valid assembly language for this microcontroller, but we'll get it in. We'll get into that later, and then move Y into register 2. Because typically microprocessors can't directly add to data values from memory and store it back in a third location. There's no single assembly language instruction to do that or corresponding machine code instruction. So these lines you write in C typically translate into several, each C line typically translates into several different assembly lines. Now at this point, you might be able to do add R1 and R2 and store in R3, and then finally move R3 into Z. So that single line in C might be translated into multiple assembly lines. Okay. Now, ultimately what happens though is what the processor understands is, and this is what makes up your program, your executable program, is the machine code binary instructions. Okay. And so this might be for 32-bit words, I'm just making stuff up, might correspond to this particular instruction. Part of that probably represents the move. Part of it may have the actual address of wherever this X variable is stored, and part of it means move that into R1. Okay, and then the next instruction, because it's got different source and destination registers, is going to be encoded as a different machine code instruction. Okay, so when you look at your executable file, you see bytes like this. Bytes, well, it's ones and zeros again. Hexadecimal is just convenient notation to represent the ones and zeros that make up the machine code. But there's a one-to-one correspondence between every assembly language statement and every machine code. Okay. Assembly is really just human-readable machine code. So we can, and we will, actually write programs at the assembly language level. You don't want to directly write in the machine code level. Looking up, okay, what's the move instruction? How do I encode an address? How do I encode the register? and write the binary ones and zeros. Okay, that's painful. Okay. The first computers were actually programmed that way, but the first computer programs were probably less than 100 lines long. So, but they would do that by flipping switches. It's painful to do that. And then, you know, probably the next generation of computers were programmed in assembly. So again, you would type these instructions into a text file and then run an assembler to convert the text into machine code that the microprocessor understands. Okay. And it's certainly a lot easier to see what's going on, what the program does at the assembly language level than at the machine code level. But every instruction in assembly gets directly encoded into machine code. And you can also disassemble, you know, machine code back to assembly. Okay. So there are disassemblers that will read your machine code and produce the corresponding assembly. And C is what's called a high-level language. There are other high-level languages, Java, C++. Fortran is an old one, that are higher level. They don't directly, each instruction in C doesn't directly go into machine code, but actually makes up several lines of machine code. So some terminology. You have a compiler that translates your C source, well, not C necessarily. It's a C++ compiler, but source code to, now at one time, a compiler might translate the C to assembly, and then you would run an assembler to actually then create the machine code. But typically, most compilers today go directly from source code to machine code. Or if there is an intermediate step of producing assembly, that's kind of hidden from you. Most compilers optionally will show you the assembly language translation. Okay, there's a flag to, like the compiler, to say, give me an assembly language listing of the corresponding machine code. That's a good way to actually learn assembly. There are, so again, compiled languages like C++, C, Fortran. Java is a compiled language, but it also uses something called a virtual machine. So it's a little bit in a category of its own. It's not quite like C. Assembler takes assembly into machine code. Now, C and these higher level languages are also said to be portable. Okay. In your C language statement, you never directly refer to processor registers. Okay. You have statements that look like this. They're based on variables, okay, typically. To write in assembly, the assembly language actually differs processor to processor. The syntax of these statements may be different. The number of registers you have is typically different. You know, some it's R1 through R16. And the original Intel processor, they were A, B, C, and D registers, okay, and E and F instead of numbered. The operations that you can do are different. So this assembly language is usually directly tied to the microprocessor that you're using, whereas the high-level languages are not. There's no reference to specific registers. So you run a compiler on say, an Intel processor machine, it produces Intel assembly and ultimately Intel machine code. But if you run that same C source code on a Motorola processor machine, it will produce a completely different set of, completely different executable. It'll produce machine code for the Motorola processor. Hopefully, you know, if you're working at the C language level, you'll get the same output from both programs. You also have what are called interpreted languages and interpreters. So an interpreter is really a program that reads source code and carries out those instructions. But instead of directly producing machine code, the interpreter reads the language line by line typically, and then carries out the instructions. So it directly runs a high-level language. Now, again, ultimately, all the microprocessor understands is machine code, okay? But the interpreter would read, some operation like add two numbers, and then it would have special instructions, a function to add two numbers that ultimately gets called into, that gets run as machine code. Some examples of interpreted languages are MATLAB, Octave, Python is another one, Perl is another one. An older computer language called BASIC was usually interpreted. Sometimes there were BASIC compilers that also existed. The disadvantages of interpreters: interpreted languages are typically slower than compiled languages because there's this extra step of read the instruction, carry it out, then go back and read the next instruction. Where compiled languages, reads your entire source code, translates all of that directly to machine code and runs that. So interpreted languages are typically run slower than compiled languages. Our microprocessors have gotten to be so fast that it's not much of a argument for not using interpreted languages anymore. And programs like MATLAB and Python, they have such high-level statements like to compute a fast Fourier transform or something. You wouldn't want to write that. You've got all these libraries that are built into the language that make it really convenient to program in that language, to do graphics, to do signal processing, to do image processing. So it's a lot easier from a user standpoint maybe to use one of the interpreted languages. For more complex projects, our executable doesn't consist of translated source code from one file, but maybe tens of files or hundreds of files. Or on very complex projects, maybe thousands of different source code files that are written by different people in an organization. Okay? I know those of you in computer engineering take a software engineering class. It's all about software design, or maybe some of you have taken that already. You take a software engineering class, it's about design of complex systems and how do you coordinate that. But then you actually have a linker that takes object modules to produce an executable, as opposed to having one source code file. We'll certainly be running several applications where we may have 3 or 4 or 5 source code files, different C files that make up our project, but probably we won't be running into cases where we have hundreds of different files that all need to be linked together to produce one executable. There's a loader then that takes the executable and then loads it into a memory on your computer, or we transfer it into flash ROM on our microcontroller. That's the purpose of the loader. And then we also have have a debugger that allows us to observe a running program. So with a debugger, you can single step through your code, right, looking at the output of every instruction. You can see how variables in memory are being changed as you step through your source code, how registers are changed. You can look at the registers. And then hopefully with debugging and stepping through, you can find where a bug in your program exists. So we'll actually be using the debugger in here so the debugger in this integrated developer environment actually works with the microcontroller so that we can single step through the code in our microcontroller and actually see the changes reflected in the debugger. So basic program structure. You would typically start out every file with a few lines of documentation. I'm using / here as a comment line in C. I think it's same comment works in C++ and Java. I don't actually program in C#. I think it works in C# as well, right? So typically here you would have, the purpose of the code that's in the file. Now the file might have several functions in it, and then so before every function, you should have a description of what that particular function does. And then at the beginning, at least, you should also include, your name, date. Typically here, if you're writing code that's to be distributed, you'd include, an email address, some way for someone to reach you. Then I'm just using an asterisk here to indicate different sections. The preprocessor. So here's where you would have different lines that usually start with the hashtag symbol, the pound symbol, or the octothorpe, or whatever you want to call it, the little tic-tac-toe symbol. These are preprocessor lines. Typically here you'd have includes and defines. What an include file does, there's actually a program that runs before the compiler. It's called a preprocessor. It reads your source code. It sees a line like this. It goes out and includes the entire contents of this header file into your source file, and then passes that on to the compiler. So it reads this entire file, and makes it part of yours, but it contains pre-written code. So you don't have to include just header files. You can actually, it's one way to include C code from another file. Typically, you don't use this method for that though. And header files typically contain function declarations, function prototypes. And then there may be another section that contains global variables. I'm going to skip that and come right to our code section. Our C programs always have a main statement. Actually, this is not the first set of instructions you'll see on our microcontroller. There's some assembly language that's actually run before our main, and then that assembly language code ultimately calls this main function, and then we'll have something like printf. Usually not printf in microcontrollers, but so every C statement ends with a semicolon. You can have multiple C statements on a single source code line, but they all have to have a semicolon. So semicolon is part of the syntax in C, unlike in Octave or MATLAB, where it's optional, and it has a different purpose. It means actually display the result of this back to the command window or not. And then one other difference in when we write microcontrollers versus code for microcontroller versus code for a PC is there's typically some endless loop here, okay? Or our code continues forever when we're writing microcontroller. Like, unlike on a PC, we write a program, it finishes, and then we get our command window prompt back. On a microcontroller, there is no operating system running, at least on the program we're doing here. And so there's nowhere to go after the program finishes. So on our microcontroller, typically our main programs always have some sort of infinite loop. Now there may be stuff, and often is, going on inside this infinite loop. Okay, this is one way to write an infinite loop, while one. Okay. You could also do it with a for statement. Okay. And then this is just an empty body. Just do this forever. So this is all the microcontroller would do. This is in multitasking operating systems, you typically want to avoid infinite loops like this, so that if you've got other tasks that are running, instead of this task tying up processor time, you'd run other tasks. And then I'm titling this control structures because that's what he titles this section in the book, but I really don't want to talk about control structures, but rather introduce you to, and I think you've seen it before, some of the binary operators that we commonly use when we're programming microcontrollers. So these are some example programs out of this section of the book, but one he has is check P3 to void. And the void here just means this particular function doesn't take any arguments. Okay. And if you look at, this is actually program 2.4 on page 74 of your book. P3 dash N and 0x04, that's equal to 0. Then out equal 0. Else 4 out is equal to program 2.4 on page 79. Page 79. Okay, you'll see a lot of, and we'll be using a lot of binary operators like and or. And is used to mask off particular bits. So I'm not going to get into all the details here. This whole next chapter, in chapter 3, which we'll start on Wednesday, talks about the microprocessor architecture. What registers make up the microprocessor, what ports are available. But this microprocessor has several digital I/O ports. You can access a byte of data at a time as either input ports or output port. And then P3 here, we'll see this notation means give me the input register for port P3. That's what this notation means, P3 with an arrow N. So what this is going to do is read from that, it's a set of 8 pins on our microcontroller. It will read an 8-bit value. Now, what is that 8-bit value? It depends on what you've got connected, wired to that port on the microcontroller. You know, if you've got some of the pins wired high, some low, or if you've got switches connected, like we talked about last time, you know, it depends on what it reads. It's going to depend on the state of the switch, whether it's pressed or not, or on or off. Or it might be connected up to some temperature sensor that outputs an 8-bit value that we want to read in. Now, the question is, what is this doing? This, you know, this is an 8-bit value, and then we're ANDing it with 0x04. So do you know what that is doing? And then we're seeing if that's equal to 0. Any idea what that's doing? Well, so ANDing is a common operation. Okay. So if you AND any value with, and I'm going to, with 1, you get that same value, right? If A is 0 and 1 is 0, 1 and 1 is 1. So any value ANDed with 1 is A. Any value ANDed with 0 is always 0, right? So this particular operation is a masking operation. So if we looked at P3N, and it's an 8-bit value, it's called the bits 0 through 7. That's the typical convention instead of 1 through 8. B6, B5, B4. And then we're ANDing. This is a binary AND. So it's going to AND each bit in this 8-bit number with this 8-bit value. So 4 is going to be that. So what does this ANDing operation do? Well, anything ANDed with 0 is 0. So we're really ignoring all of these bits except B2. B2 ANDed with 1 is B2. Now, so this thing is going to have 2 possible values, right? Depends on whether B2 is 0 or 1. If B2 is 0, what is this 8-bit value equal to? What's this 8-bit result? 0, right? If it's 1, what would the 8-bit result be? 4, okay. There are only those 2 possible values here when I do this ANDing. In this case, this is just checking if that bit is 0 or not. Right? So in this case, the only way that ANDing result will be 0 is if B2 is 0. All the other bits are actually not even relevant. I could, you know, check maybe to see if, you know, B5 is 0 or not. You know, I would AND then with OX20, right, to check B5. Or I could check to see if both B5 and B2 were both 0 by ANDing with 4, OX24. In that case, there's 4 possibilities though. They could either both be 0, which I'd get 0, or they could both be 1, I'd get 1 result, or 1 could be 1 and the other would be 0. Okay, there'd be 4 possible outcomes there. But here, this is a common way to check to see, you know, if a pin on an input port is 1 or 0. If it's 0, I'm setting port 4 to 0. If this pin is 1, I'm setting port 4 to OXAA, which is 1010, 1010, okay, or whatever values you would use. So this ANDing operation or masking operation is pretty common when we're reading input pins. Okay. We want to determine whether one bit is 0 or 1. Another common operation is actually setting an output port bit. Let's say we want to set bit 6 in P4. Let's say we want to do that in such a way that we don't want to change the value of any other bits. So this is not going to work. Bit 6, that would be, right? That's not going to do it. That would set bit 6, right? But it would set all the other bits there to 0. So if we don't want to leave the other bits unchanged, what you would typically do is read P4 out, read that register value, and then OR that with 0x, what did I say, 40. So that's another common operation. Okay. Now, what does ORing with 0 do? A ORed with 0, what is that always equal to? It's equal to A always, right? 1 ORed with 0 is 1, 0 ORed with 0 is 1. But it doesn't matter what A is, whether it's 1 or 0, we get A back. So ORing with 0 is not going to change any of those values. But what does ORing with 1 do always? What's A ORed with 1? It's always 1. Right? So this will be sure, it doesn't matter what bit 6 was, whether it's 0 or 1, I don't care. The output of this would be, you know, B6 would be 1 and all the other bits would be unchanged. Okay, so this is kind of another common operation that we'll be doing when we need to set a bit in a particular register and leave all the other bits unchanged. He has another example here. So what does exclusive ORing with 1 do? Yeah, it's always going to be A naught, right? 0 or 1 is 0, 1 or 1 is 0 or 1 is 0 exclusive or 1 is 1, 1 exclusive or 1 is 0. So A exclusive or 1 is always A bar, the inverse of A. So that's going to flip a bit. So he has an example program in here where he toggles a bit every time he goes through a loop. Just wants to flip it back and forth. Easy way to do that is just, and the code he has in this loop, this is program 2.6, but he writes this as P4-out is equal to P4-out, and then exclusive OR 0x08. So what bit is that toggling? The 4th bit, which is the 3rd bit, which is B3. Yeah, 4th bit, which is B3. What's going on with the other bits? What's A exclusive or 0? It's A, right? So the other bits here are being unaffected. And we're not changing those at all, but this operation is toggling B3. Now, actually, in this code, he writes this as That's just compiled syntax shorthand. This represents P4 out is equal to P4 out exclusive word with that. Similarly, we're going to have, you could write this one as P4 out or equal OX40. Yeah, it's shorthand notation. It means the same as that. Actually, I tend to use this notation. It translates into the same machine code instruction. There's no savings. I just think that's a little clearer. The longer notation is a little clearer than the shorthand notation. This saves you some typing when you're producing the source code. Okay, so I wanted to try and go through. Looks like mine's still installing. I think I can connect to my desktop upstairs, though. Always point at that one when it's back here. Yeah, mine's finally got past that one jar file, and it's on to doing, it's running some eclipse.exe now. So I think it's about done with the installation. These are pretty old computers, and they're slow. So it still hasn't installed yet. This is going to be painfully slow. Hope I've got nothing on my desktop that's going to embarrass me. Okay, looks like actually I had this up. So good, okay. So I'll go through the whole process. So I don't know if it puts this icon on your desktop or it's in your start menu, but it's this Code Composer Studio. It looks like this little die. So then when you start it up, I think I left the microcontroller connected to my desktop upstairs. Because this is actually running on my computer up in my office. And so it will be sending the executable file to the microcontroller connected to that machine. Now, so typically what we're going to do, what I want us to do in the homework for this first exercise is we typically want to say new and then CCS project, Code Composer Studio project. And then for the target, now mine already has it here because I've run this before. It says MSP432P401R, which is our microcontroller, right? So you've got a list of other ones there, but you want to make sure that you select the right one. And then I'm going to call this hello 2. I've already got a hello world. Okay. And then the project name. And then this is actually going to be stored in your workspace. It'll create this new directory. And it shows you here where if you've got this use default location check, mine's on my F drive, AR63, workspace version 10 of the Code Composer Studio hello 2, and then finish. And and then it will actually create looks like I can't resize it with my mouse. Can you see that? Kind of an empty program at this point. It's got one line in it. The one line of code is to actually, our microcontroller has what's known as a watchdog timer on it. If it doesn't reset the watchdog timer, then your microcontroller reboots. Okay, so that's the guard against you running code that gets stuck in an infinite loop or something. We want to disable that, and that's what this line does. It does that for you automatically. So here, we want to, I'm going to have an infinite loop while one, and then printf hello world /n. So this is just going to print that over and over and over as fast as it can. Now, question is, where does this printf go to? Well, by default with this printf, it actually stores the string in a buffer and then sets a breakpoint on the debugger. So you're actually only going to see this output right now when you run this program in the debugger. Okay, you won't, if you just run it, you won't see this output at all. Okay, but if you run it in the debugger, you will. We'll look at, maybe next time or in the future, how to actually, there is a virtual serial port here on these microcontrollers so that we can connect via terminal to our microcontroller, and then we can have the microcontroller send the printf output to that virtual serial port. But right now, we'll only see it in the debugger. So if we build the project, hopefully this will build without any errors. Okay, it looks like I got one warning somewhere. Printf declared implicitly. That's because I didn't include, the standard io.h. It would have run fine, but try to eliminate all your warnings. Okay, and so it looks like finish this time without any warnings. And then now click on the little bug. Okay, looks like a tick to me, but click on that little bug and you'll go into debug mode. Now, it takes a while to make this transition. And actually, when it comes up, finally, it's still not here. Now I'm finally here. It's actually stopped, I think, at main. Okay. But if I click on the little green arrow to actually start running, you see the output here in the debugger console window. So I'll give you, the homework problem will be related to this for today, is to actually make sure you get code running under Code Composer Studio on your microcontroller by Wednesday, okay? And something like this. So if you have any issues, stop in and see me later today or tomorrow. Tomorrow I'm pretty much free all day. Okay? And then click on the little red box here to stop the debugger. And it looked like mine finally finished installing. It says a reboot is required.